Hey guys, welcome back to our traffic course CE432, and here we'll continue reviewing our statistical analysis for traffic engineers. In this video we'll talk about normal distribution. It's a continuation to video number 8, this is video number B. So let's start directly and learn how to deal with normal distribution questions and how to solve normal distribution problems, which most of the traffic data goes around. We're going to talk also about other kinds of distributions that we use a lot in traffic engineering. So again, the word distribution, let me just bring my here. So the word distribution again is some kind of a model in which we try to fit our data to become an equation, so we can find values that you expect in the future. This is the total meaning of statistics: how to use data and how to fit it in some kind of a distribution, or another name for it is a model, in which you try to say, yeah, your data follows that, and based on that I can know if I have future data, how much will it be, what will it fit, what is the probable value of that. That's the meaning of the word statistics. And as we said before, most of our random variables, again, the word random variable is a variable that can take any random number. Any human work, any traffic work, usually is a random variable. In other words, if you want to figure out what are the speeds, no two speeds will be the same. If you just measure the speeds right now on the road out of your house right now, two cars, they won't be the same. They're random, they're different. So we try to get some speeds, we try to collect data using statistics, we try to figure out what distribution it is, so I can say, yeah, this road, the speed there follows this kind of distribution, and this distribution has very simple characteristics which we'll be discussing today. So that's the meaning of the word distribution. So one of the most famous distributions is this guy here, the bell curve. It's called the normal distribution. It was developed by Gauss. That's why they also call it the Gaussian distribution. We don't worry about the name. And this was the equation Mr. Gauss has created. Will I ask you to start working on this equation? Definitely not. I'm going to have a shortcut to that. What does this tell you? It tells me that the values fx, which is in our case it's the frequency, how many observations for every value. For example, here, if the speed, let's get back to the speed, is 65 and 68. How many vehicles will have these values? And that is what we get here, and that's how we calculate it. However, we're not going to that, we're going to do some kind of shortcut. But let's learn how to define a normal distribution. So x here is a statistic which is random, and we talked about speed, height, weight, whatever variable that's normal. Here's something we call the mu, and mu is what we calculated in our first video. Mu is the same name of your x bar, which is mu. So notice something: once you have your data, your statistics, you try to figure out the mean of it. What is the value, the central tendency? What are the when you, for example, calculate the heights of you guys in class? You say, yeah, it's around 5 feet 8. People are shorter or longer, or taller, but still you have this average. So the average is one thing that we use a lot. And then the standard deviation, which also we talked about. So here mu and mu and sigma, these are the two different values you have. One thing we have to put in the table that you want to, also you might remember this from statistics. In case you are using a sample, then you use either x bar or m. That's a sample. So when I go collect the data, you get this. You don't get the actual number of cars going 365. or the actual speeds for everyone. And when you have the whole population, sometimes we can do that. This M turns into mu, turns into like this Latin letters. Also, S is your standard deviation. Just give it a letter S if we're using sample. And the variance is S squared equal to variance. When we use the whole population, let's imagine we're going to use the whole data. This S turns into this sigma. And sigma squared also equals to variance. So when we have different types of letters, they're probably almost the same. It just depends on what are you calculating. So when we have the number 1, and this is how we define your normal curve. Number 1, what is the x value, the number that your values are around? 5'8" in case of height, 55.2 miles per hour in case of speeds on a road. And then you figure out, okay, how much spread is your statistic? Do we have cars that are very, very fast and cars that are very, very slow that will make your curve a little bit spread? Or is it all cramped around this mean? So this will give you what we call here the standard deviation. We talked about this in video number 1. And here, knowing the standard deviation and the mean will give you this kind of curve. So we write it as you can see here. N, which stands for normal curve, follows the distribution. So your data, we say here your x, which is the variable, follows a distribution, which is normal, which has a mean of this number, mu, or x bar, and the standard deviation square, which is the variance of standard deviation. So when you have a sample, you calculate number 1, the mean, and you say my x follows a normal distribution that follows a mean x bar, which you calculated from your data, and also you calculate the standard deviation, and this for the variance and the standard deviation, we call it now S, in case of your sample, S. Okay, so it's called normal distribution. X follows this, it's bell-shaped or Gaussian shape, and we call it also a bell-shaped probability density. Why density? Because in the y-axis you follow the probability of how many people will be there. So you count, and the counts will give you the probability. And that's kind of the heart of statistics. I hope you guys understand it, and it makes it a little bit easy, and you can use it in abstract engineering. So what's a normal distribution? It's centered about its mean. Spread of function is what we call the standard deviation. Mean, median, mode are kind of equal. What's the mean by that? Here we have tons of data, thousands of data. So when we do it, you're going to find that when you have data, the mean, remember we did the mean, which is the number of observations, the sum of observations divided by n, so that's what the mean. And when we did the median, and just to find with the median, you arrange the data in some kind of an order, and you just find the middle value. When you have tons of data, thousands of data, you're going to find, and you arrange this, you're going to find these guys are almost the same. And then the mode. Well, since most of the data goes around this central value, then the most repetitive value is going to be the central, once you have thousands of data. And here comes thing we use a lot. This is what I told you here. This is a shortcut. We found the following. When you have the mean, the bell curve, a typical normal distribution, and now we're talking here about density, or we're talking about the probability. And you measure here 1 sigma for standard deviation and a -1 sigma. You're going to notice that the area under this curve will be equal to 68.27. First of all, what's the meaning of probability? Probability that the next observation you take, the next speed you're going to measure, the next person you're going to measure his height, will fall between these two values, between -sigma and +sigma. So let me tell you here, an example. Let's say we measure the speed on the road, and the mean was 50, and the standard deviation was 5. So negative sigma is 45, just subtract 5, and here 55. So the probability that the next person or the next car coming that will have a speed between 45 and 55, not speeding, not slowing, is around 68.27%. That's one of the characteristics of the normal curve. And we get it from this histogram. Histogram is the repetitive values we count, and we find the variable, and then from it you get the probability. And that's how spread it is. And one thing you have to know, the probability that from negative infinity to positive infinity, probability that the next car will have a speed, that's the other way to say it, is 100%. One. So always your distribution covers 100%. A 1 probability that, yeah, what's the probability that I'm gonna have speeds from 0 to 200 miles per hour? That's everybody will have this thing. But I'm talking here about very smaller value, between 45 and 55. So that's what we call here 68.27. So if you measure another 5, because you have here 2 standard deviations, so when I have here 2 standard deviations, so when I measure here, instead of 55 I go 60, and instead of 45 I go 40, I'm almost 95% sure, or 95% of probable that the next person will be between 40 and 60. So here I have more range and you have higher probability. Let's talk now between 35, and that's the most probable, you can see here. So for 35 to 60, here I added 3 standard deviations this way and 3 standard deviations that. It's gonna be 99.73% sure that the next person will have the speeds between these values. So we're gonna take these observation probabilities, and use them as a shortcut. Instead of going to the equation of the normal curve, we're gonna use this for a shortcut, just to give you an idea what is the meaning of standard deviation. So you can gives you an idea also, if you have a big standard deviation, the numbers are very spread. If you have a smaller standard deviation, the numbers are all around this mean or this average value. So what's a normal distribution? Again, it's the probability of occurrence between any values x1 and x2. So what's the meaning of that? Since we're doing here a probability, we're talking here that the area under the curve. So probability here in a normal curve or any kind of distribution is the area under the curve. So when I say here what's the probability that the speed between 40 and 60 or between 70 and 80 will be. So what I do is that I find here in our equation, I do some kind of integration to find the area under the curve. This will give you the probability that the speed between x1 and x2, whatever the values are. So that's the simple way of doing it. Again, the area under the curve from negative infinity to plus infinity is always 100%. This is how we do the normal curve. So the area is always obtained by some kind of integration. Since it's very hard for us to integrate, I know that, especially for this equation that I showed you, we use our beautiful handout here, this guy. These are famous charts of normal curve, and they give us some kind of a transformation between x1 and x2 that you have, and area between the curve. It gives you the area, and from that you will know the probability that the next values are there. Most of statistical equations depend on some kind of these tables. They are very straightforward, and the way to do it is easy. I'm going to do it step by step with you, and a huge part of your homework is how to use this chart step by step. Let me show you here what I mean. So this is how we do it. The integration cannot be done, it's very complex, so we use something called a normal distribution, or something called a standard normal distribution. In other words, this is your curve. You have here a mean of whatever x you calculated, and a sigma of whatever sigma you calculated, whatever standard deviation. We're going to transform this curve into a similar equivalent curve but with different values, and then use the table to calculate the area under the curve. What is this curve? Instead of x, I'm going to say here this will be a 0. Why 0? Because we again want to find the area under the curve. And instead of your sigma, this will be 1. So you can see here on an normal distribution, and instead of using x, let's use now another variable called z, and it's another random variable that goes also from -infinity to +infinity, and the mean value is 0, so that's a z. So x will be equivalent to 0, but the normal distribution will be a bit different in terms of just the standard deviation and the mean, but we're gonna do some kind of transformation back and forth, and this is our shortcut. So what does it mean? I have here a curve with your x with the mean. I'm gonna find the equivalent. It's gonna be the same line here with a 0 in the next standard normal distribution, and if this was sigma, whatever number it is, 5 miles per hour like we did in the previous example, to a just 1. So here your x, which follows a normal distribution of mu or whatever, x bar or mu, and sigma squared is your variance, will be transferred into z, another variable, which follows a normal distribution. So that's x bar, and it has -0 and a standard deviation. Then I calculate the probability. The probability here will be the same. I'm going to calculate the probability here using the tables, and then I can later on get back to the x value. This is the shortcut we do. What is the transformation? This is it. x minus mu over sigma. And if we're using a sample, z equals x, whatever x value you have, minus x bar of your data, divided by s, standard deviation. So it's an equivalent statistics that we use, and the tables that I just showed you, let me go back to this table here. So the table that we use here, you can see here is the z-value. So this is the equation. We should do some kind of integration, and what you can see here, the numbers here, we have the z-values on the first column and the first row. I'm going to tell you how we use it, and we transfer this into the probability. I'm going to say that that's the fact. The probability here is equivalent to the probability of the value you have. So we do this transformation, and then we will do it again. So let me solve a question. It's so simple, guys. Very, very simple. So a speed spot collected on Highway 61 indicated that the average speed was 50. So here, this will be the question. Here I have x bar equals 50, and the variance. And make sure you make a difference between the word variance and standard deviation. Variance is 49, so my standard deviation is square root of 49, which is equal to 6. What is the probability? Let's draw here the curve. So here, this is how it works. The mean is 55, and the standard deviation is +7, so it's 55 plus 7, 62, and 55 minus 7 is 14. So here these are the first standard deviations. Sigma, or let's call it s. Sigma or s should be the same. And this is in miles per hour. And this is also in miles per hour. What is the probability that the next observed speed will be, let me do it in a better way, will be 60. This is I'm doing it really, really bad, but this should be a symmetric curve. will be 65 or less. So that's 65 or less. And the curve that I showed you, the Z curves, always talk about less. And we can find tricks now if it's more. So I want to find here what is the area for the curve if it's 65 or less. So the first thing, before we go into the table, we want to calculate the Z statistic. This 65, what is equivalent to in the Z statistical curve? So when I created this kind of standard curve where this one is 1, 0, and the standard deviation is 1, I want to know with this 65, what is equivalent to the Z distribution? And then I go to the tables and calculate the area of this Z distribution. So we calculate the Z value of x equals 65 miles per hour, which is equal to, let's do it together. X here is my 65, so 65 minus the mu here, or the x bar, is 55 divided by 7. So it's equal to 10 divided by 7. Let me give you the exact value of 10 divided by 7. I'm just going to do it so fast. So it's 10 divided by 7 equals. So my Z value equals 1.428. Okay, now let's go to the table and figure out where is the, and how you calculate now. So here you go to this table here. How to do it? In the first row, you're gonna find values of Z just to the first decimal place. So here I want 1.428. So I go here 1.4. So this is 1.4. Okay, this is 1.4. And then I want 428. So it's between 1.142 and 1.43. So you go here, it's between these two numbers. So it's equal to some number between 0.92222 and 0.9236. But it's closer to 0.9236. So the probability, let's get that here. So the probability here is equal to some number here between 0.9222 and 0.9236. That's for 1.42, and that's for 1.42. And then you can do a very simple interpolation to find for 1.42, let's say 9. Or you can just do it by your eye. So the probability here, let's just say here is equal to the probability that's going to be 65 or less. It will be equal to 0.9 to, let's say 29 or 0.9. I can do it by interpolation, which gives you an exact 92%. In other words, the probability that the next car will be 65 miles per hour or less is 92.3%. That is how we do it. Question number 2 here, like this part here. Okay, what if I want to know the speed if it's between 55 and 65. Again, it's 55 and 65. Let me tell you first how we do it using the table. If you notice here that the table always talks about if it's the value or less. This is the probability, if it's a number or less. And because this curve is symmetric, if I wanted this number or more, it's 1 minus. If this whole is 100%, it's minus this area, gives you the small area there. So it's so easy for us to use the same with some tricks to find it more than. And also in this case here, when I want to find two values, well, I do it without even using the table now, because I know that from 65 to negative infinity, it's 92.3%. And 55 is exactly in the middle, so this is 50%. Right? The average is always in the middle. More of this is 50%, less of this is 50%. So between 55 and 65 is all this area minus this area, which is the small area here. So it's equal to 92.3% minus 50%, which gives you 42.3%. See how guys is easy? If it's another value, if it's 57, then you're gonna have to go to the table twice, because I'm gonna find the area here and the area here, and you calculate the difference. And that's how, guys, we do this normal table shortcut using the table that I gave you in campus and also in class. This table is available in any statistical textbook, and it's available also online if you just search for the normal curve or the normal distribution tables. Okay, guys? Based on that, we talk here about the probabilities, and we talk here about different areas under the curve with different sigmas. So here when I have here negative sigma, or 2 sigma, or 3 sigma, and plus sigma. Here we create what we call here confidence bound. What's the confidence bound? It's how confident you are when you put a statement about your data. So when I say here that, yeah, I'm 95% sure, and that's here the confidence, that the next car will be between, let's say, 40 and 60, like we did before. So this is what we call here the confidence bounds. So here when we talk here about the confidence bound, we talk about our mean, the value that we calculated. How sure we are that this number is, we're confident that it's going to be true, and based on this, and this here comes the word probability. Probability here gives you some kind of confidence. When I say here, yeah, I'm 95% sure that the next card will be between 40 and 60. And this is what we call here the confidence bound. Well, then let's talk a bit more. This kind of might be a little bit complicated here when we're talking about confidence bound. Sometimes we have more data that are distributed in more different ways. And let's imagine that you guys in class, we have 6 people here, and each one of you measured 50 speeds, and each of you have a mean. Then I get the mean from each one of you, and these means will be definitely normally distributed. So let's say here 50 each one of you, so I have 50, that's 300 observations, and I want to calculate now this mean of the means and the standard deviation of the means. So your mean will be also normally distributed. So I'm trying here, the more data I collect, the more people I have and using data, the more accuracy you have. So here, just the difference here, since I asked 6 of you to collect the data, instead of using the standard deviation, we'll be using something called standard error, E, of the mean. So here, I calculated 6 means from 6 of you guys, and the standard deviation of your means, so I get to calculate for your means, your standard deviation of the means. I divide here by number of n, which is 6 here, square root of n, which gives you the standard error of everybody here. And here comes now the standard, the confidence zone. This is how we calculate it. Here, this is how we do it. Your true mean, and this is what we're trying to calculate when I find the means of 6 people of 50 different observations. I'm trying to get this true mean, and here comes the difference between you and x bar is equal to the x bar of each one of you. So here you calculated the means. I try to find the mean of every one of you guys, and then plus or minus what is the z-value of this confidence interval of sigma over 2, I'm going to tell you what sigma over 2 in a second, multiplied by this standard error, which is the standard deviation. So this is how we do it. This z sigma over 2 tells you, like we did before, if it's 1 standard deviation, 2 standard deviations, or 3 standard deviations, or 1.96 standard deviations, that will give you a 95% or a 93%, like we did in the previous slide, where it said 68% if it's 1 sigma, 95% if it's 2 sigma, 99% or 99.5% is 3 sigma. This is exactly what we'll be doing here. We're going to use the z-values from the table and we multiply it by this standard error, and we subtract or minus it to our mean that we got, in case we had different means of observations from different people. And let me show you now this here. So again, when we have 1e, 68.3%. When we have almost 2, we have exactly 95% confidence. Or when we say the 3e, we have 99.7% confidence. So here, z, this is called here a two-tailed z-value. When we have here your standard deviation, when we talk here about when you have a value, this is the other side. We call this a tail. And surprisingly, if we have the 2 plus or minus, this will be have here 2 tails. The 2 tails, if I add them, they should be the same value because I have here plus whatever sigma and minus whatever sigma. These tails should be the same. We call it also sigma over 2. So z subscript sigma over 2. Actually, this is it's alpha over 2. Z subscript alpha over 2 is a two-tailed z-value of alpha level of significance. So at 95% confidence, at alpha level of significant, 5%, then this is equal to 5% divided by 2, 0.025. Or in other words, this would be 0.975 in our table, or in our standard normal distribution. So we go ahead, if you look in the table about this 0.975, like I'm going to show you right now. So here I'm looking for 0.975, somewhere here in between. Sorry, 0.975. So here it is, 0.975. That's the probability. So I go here, you're going to find here at 1.96. So again, what does this mean? It means that the probability that you have here is 97.5. If I have here 1.96 plus and 1.96 negative gives you exactly 97.5 yeah, sorry, I made a mistake, guys, here. If I have here, let me do it again. If I have a 5% sigma, then this guy here will become 97.5, and the area here under the curve will be 2.5%, right? But I'm here having a 95%, so here I'm going to have here a 2.5%. So the area under the curve will be equal to 95%. And the value here will be equal to 1.96 and 1.96, negative 1.96. In other words, if you have a z-value between negative 1.96 and plus 1.96, I'm 95% sure that the next value will be in this area. Or if I'm using here 99.7 confidence, here I'm using 3 and 3, so here I'm sure that between plus 3 and minus 3, I'm 99.7 sure that the z-value will be equal to these, between these values, negative 3 and plus 3 for the standard z-value. And also we call this part here, we call it the tolerance. So this part here, the plus or minus, we call this the tolerance. We give it also symbol of small e. So how do you do it? First of all, we calculate the mean, sometimes the mean of the means. Then we calculate the standard deviation of your means, and then you put here 1.9603, so you become 95% or 99.7% sure that this value is the normal. So this is a very important part. This is what we use a lot. So let me give you an example here. So let's say I have here a 54 speed observations, and the mean here, let me draw the curve. So here I have the mean is equal to 47.8, and the standard deviation is 97.80, and I have 54 observations. So I want to figure out what are the confidence bounds. So first thing, we use this equation here to calculate this tolerance, and we're going to use here, since we're using 95, so this Z alpha over 2 will be equal to 6. So this is how, so to get these constants, so we calculate here E is equal to 7.8, the standard deviation, divided by square root of x4. That's and your true mean, which I never know, is going to be equal to 47.8 plus or minus, these are my 95% confidence bounds, 1.6 times this value, and this is how we calculate the confidence bounds for our I'm gonna do more of this confidence bounds on Wednesday class, but I just want to give you some kind of heads up of how to use that. We use this a lot when we want to figure out how many samples do you need. I won't do this in this class, but once you get into graduate statistical class, you'll be doing a lot of these, giving you an idea, okay, how much time should I stay there? How many cars minimum should I count to get a 95% confidence in my data? This is how we do it, and it comes from the equation we just did. We use here 1.96 if it's 95%. This is n has to be always more number of observations, has always more than the result of this equation. We won't do it in this class. I'm going to leave it to a graduate class. So an example here, just to show you how we do it, we have here, we give you the tolerance, the standard deviation, and what's for 95%, we use 1.96, and it will give me the value of that. Okay guys? So I'm gonna skip some parts here, but I don't want to go into lots of your statistical chapter in the book, because again, I know you are traffic engineers, you want to skip directly into traffic engineering. So let's move now to some of other distributions that we use a lot in traffic engineering. I'm going to review these and then solve some questions together. So there are, when we talk here about some kind of just to remind you, we have two types of distribution, two types of random variables. We have continuous and we have discrete. So here, for x can be continuous, for example speeds, or it can be discrete. For example, number of people waiting in a toll booth. So this is discrete. So here for discrete, we use other kinds of distributions here, like we talked about last time. For example, something called the Bernoulli distribution. Bernoulli is very easy. It's a yes or no. Probability that we have people, or probability we do not have people. So we have here probability that x equals 1 or x equals 0. Here we have probability p or q, and 100% minus p equals q. So we use this a lot in transportation. Remember when we talked about auto or transit, yes or no? We use here this Bernoulli distribution. Another distribution that depends on the Bernoulli is something called binomial distribution, and it's so easy, guys. Binomial distribution is observe number of outcomes of a binomial distribution. So let's say here we record the number of events that have one or two possible outcomes. This number follows a binomial distribution. For example here, let's say that I throwing a dice, and I want to know, throwing a dice, and I want to know how much time I'm gonna get a 3 in the dice. So you start counting. This count will follow this kind of binomial distribution. So the probability that x equals 1 equals p, that's for our Bernoulli. So for my binomial here, when we have here probability of your variable become, let's say I'm gonna count how many times I get a 3, then the probability I'm gonna get 4 3s is equal to the factorial of n, number of times you did it, factorials of number of n minus x, factorial times x factorial, probability of factorial. Well, let's say we want to figure out how many times, what's the probability I'm going to get 4 times. So it's 6 minus 4. Let's say I did 6 times factorial divided by factorial of x, probability of x, and here p and q are the ones you get here from the Bernoulli distribution. Times 1 minus p, n minus x. So it all depends on 3 values. Number of times you are counting, what is the probability you want to test for, and that's it. So here these are the values you want to calculate. The mean is always equal to np, probability that you're gonna get a 3. So for a dice, probability you're gonna get 3 is definitely 1 over 6, right? Have 1 over 6 probability I'm gonna get one of the sides of the dice. So when for a dice you have 1 of 6. So probability 1 of 6. So if I multiply it by 6, I did it 6 times, then I'm gonna have a probability, the mean, I'm gonna get it probably 1 time. 1 time I'm gonna get this 3. So I'm gonna ask you, what is the probability that your x will become equal to 4? It's gonna be very less probability that I'm gonna throw the dice 6 times, and out of this 6 times I'm gonna get 4 times of a 3. So that is the binomial distribution. How do you use it in traffic engineering? We use it a lot when we talk about defining the difference between public transportation and highways, and we want sometimes to count how many times people will come to a toll station. I'm giving you different examples of using these discrete variables. And again, every kind of distribution follows some kind of curve at the end, even if they're discrete. We put them as histogram like this, and this is how it works here. So if your mean is, let's say your mean is this number here, then you're gonna have less probability, you're gonna have more or less. Again, like we do in the normal distribution, but this is another distribution that we call here binomial distribution. This is the equation for that, and we do it for every single number since it's discrete, and we calculate here the mean and the variance. Again, the variance is not the standard deviation, it's square the standard deviation. The variance is n times p times q. Again, p equals the probability this number will happen, q equals 1 minus p. Again, always remember this, it's the probability of the other side. So again, if it's yes or no, then this is how we do it. Another distribution is called Poisson Distribution, and this is a very important distribution for our toll booth and queuing theory. It applies to observations per unit time. So when I say here, how many people are coming to your toll booth per time, how many people arriving at the intersection, and it's very, very important for what we call here rare events like accidents. And also you say here when x follows the Poisson distribution, and this is how the Poisson with probability of a variable. If I have here this variable x, what's the probability that you will have 3 cars in the next minute? So here e to the power of mu, and mu here is both the variance and the mean, and mu here is what we call here rate of arrival. It's like the mean. So when I count, for example, the volume on the road for an hour, the rate of arrival is 600 vehicles per hour. That's my rate of arrival. That's the mean number of values. And also it's the variance, and that's the beauty about Poisson. and I want to calculate now this probability that in the next hour I'm going to calculate, I'm going to count 800 or 600 vehicles or 500 vehicles. So this is the Poisson distribution. If the mean is not equal to the variance, then it does not follow this kind of Poisson distribution. So here an engineer counts 300, that's an example here. An engineer counts 360 vehicles per hour at a specific highway location, assuming that the arrival of vehicles highway location is Poisson distributed. Estimate probability of having 5 or more vehicles arriving over a 20-second period. How we do this? Let me show you guys. So X, it follows Poisson. We want to know what is mean. Well, we have 360 vehicles per hour, 3600 seconds. Therefore, in 20 seconds, we have a 2 vehicles arrival rate. And that's our mu here, the arrival rate that is equal to both the mean and the standard. In other words, your mean is that when you have 2 vehicles per 20 seconds. And then we calculate here this power. So here, probability that we have here x, whatever x will be, so that's will be e to the power negative u times u power x over factorial x. So this is will be the equation for any x you want. So here we want to calculate what is the probability of having 5 or more. Well, 5 or more can be infinity, but I can have 5 or less. 0, 1, 2, 3, 4, 5. Again, when I say probability of 5 or more, I cannot count 5, 6, 7, 8, 5 and until infinity. It can be infinity. But I can calculate less. So it's equal to, when I calculate the probability that no cars will come, 1 car will come every 20 seconds. 2 cars will come, 3 cars will come, because it's 5 or less. And this is the probability of 5 or less. It's equal to 1 minus 5 or more. So this is the change between those two. So this is how we do it. We put it in the table. We calculate it using the same equation we did. Probability of having 0, 1, 2, 3, or 5. And then I see here 1 minus this guy, then this guy, and then this guy, and this guy, and so on. So we calculate here. We can find that probability of having 5 or more cars is 5.27. So this is how we do it, guys. We just did it in the table with a commuter way. So you can just simply add these guys together, which give you this 0.9473. So it gives me here 5.27. Poisson, sometimes it seems hard or confusing, but believe me, guys, it's so straightforward. Here we just count what we have. We use the equation probability of having 1 value, and if it's more or less, you just use the same equation the same way we did it before in normal distribution. But here in discrete, we count the probabilities of the different values. Then we talk here about linear regression, which I'm not gonna discuss in this class. It's again, you can have a class in linear regression in your graduate course. But linear regression is another way to model the relationship between x and y. You have different sets and find the relationship. It gives you the way to do this relationship. All I want to say here is that if you remember your software tools class, when we did put a trend line for your Excel data, this trend line is a regression analysis. When you put a straight trend line, this was a linear regression analysis. So I won't go into the specifics of it because we have a really powerful tool in Excel that uses that. By this, guys, I end the statistical part, and starting next week we will talk about traffic stream analysis, which is a very nice topic to start now with traffic code. But again, we need some background to use in statistics, and I hope this gives you a very fast point. Thank you, guys, and see you in the next video. Bye bye.